Hi, this is Dr. Collins Jones. Welcome to segment 7 of my video series on measurement, significant figures, and basic data analysis. In this segment, we will discuss the rules for determining significant figures when doing simple arithmetic calculations, that is, multiplication and division, and addition and subtraction. I want to justify the rationale for this with an example. So let's calculate the rate for a chemical or an enzymatic reaction. Recall that the rate is given by the amount or distance divided by the time. So for a chemical reaction, this could be the moles of product produced per time of reaction. And there are other ways we could define the rate, right? Moles of substrate consumed and so forth. But for this example, we're going to define our rate of reaction as the moles of product produced per time of reaction. Okay? So suppose we measured that 29.73 moles of product was produced over 15.1 seconds, right, for a time of 15.1 seconds. So to do the calculation, we have moles of product divided by the time of reaction, which is 29.73 moles divided by 15.1 seconds. And when you put this into your calculator, the display reads 1.9688742 moles per second. So that answer has lots of digits, way more digits than were present in either measurement. We know we can't measure all 8 digits here, okay? So we need to correct the number of digits in the calculated answer to be consistent with the number of significant figures obtained for the measured quantities. That is 29.73 moles of product, which is 4 significant figures, and at 15.1 seconds, the time the reaction ran for, which is 3 significant figures. So when you take this into account, the actual answer would be reported as 1.97 moles per second. So let's look at the rules that allow us to determine this. For multiplication and division calculations with significant figures, when multiplying or dividing measured quantities, the answer can have only as many significant figures as the measurement with the least number of significant figures. So the measured value that has the smallest number of sig figs, that determines how many sig figs will be in the answer. So for some examples here, 3.51 millimeters times 10.5258 millimeters is going to have how many significant figures? Well, we look at each of these. Okay, 3.51 has 3 significant figures, and 10.5258 has 6 significant figures. So the 3 significant figures is going to determine how many sig figs will be in our answer. So our answer can only contain 3 significant figures. If we divide 4.2150687 mils by 10.000 minutes, the number of significant figures will be determined by, well, let's look. Okay, 4.2150687 has 8 significant figures. 10.000 has 5 significant figures, so our answer will have 5 significant figures. For any calculation, right, any calculation, use all the available digits, both significant and insignificant, during your intermediate calculations. So in other words, don't do any rounding at each calculation step. Wait until the end to do any rounding. So keep all the digits on your calculator while you're doing the calculations. Do not round until the end of the calculation. 2 or 3 roundings in the middle of multi-step calculations can drastically change the value of the answer. So don't round until the end. And then when you're going to report the final result, you round to the nearest significant digit. So let's work through some examples of this. Okay? Rounding off. Do not round off until the calculation is complete. Keep all the digits. Can't say that enough. So how do we figure out how to round off? First of all, determine the number of significant digits required in the final answer. Once all the calculations are complete, look at the digit 1 to the right of the last significant figure. If the first insignificant digit is less than 5, just delete it and all the other digits to the right of it. Okay, so here for an example, I've given you a weight with lots of digits in it. Okay, but suppose the answer only requires 4 significant figures. I just picked that at random. I could have said 3, I could have said 5, whatever. But I'm just going to suppose that our answer requires 4 significant figures. Okay, so we look at this number and we say, okay, 1, 2, 3, 4. That's as far as our answer can go, right? Those 4 digits. So now we're going to look 1 digit to the right of the last digit that would be in our answer, and we see that it's a 4, okay? And 4 is less than 5, so we just discard all the 4 and everything beyond it. And so our answer turns out to be 12.37 grams, all right? If the first insignificant digit is 5 or greater, then we increase that significant digit right before it by 1, and we delete all the insignificant figures. So you can see I've changed the number from above to be 12.375 with a bunch of zeros, all right? And again, we want 4 significant figures, all right? So we're going to look at the 5. And our rule said if the first insignificant digit is 5 or greater, then we increase the value of the last significant digit by 1. So this becomes 12.38 grams. All right, let's look at an example from start to finish, okay? Here's our calculation. 6.521 grams divided by 12.4 mils. And you might recognize that as a density calculation because density is equal to grams divided by the number of mils. So we do the calculation, plug this into our calculator, and the calculator display shows 0.52588871 grams per mil, right? Many more digits than were in either of the measured values in our calculation. So if we look at our calculation, we see that 6.521 has 4 significant figures and 12.4 has 3 significant figures. So our answer must contain 3 significant figures, okay? So now we have to do the rounding. So here's our displayed answer. We need to have 3 significant figures. We look at the digit to the right of the last significant figure. This is an 8. 8 is greater than 5, okay? And we're going to ignore all the other digits. So that's the only thing we care about. And so our correct rounded up answer will be 0.526 grams per mil. Okay, so first of all, let's do some round off practice, okay? So again, I'm going to count to 3 here. You can pause the video and then try to work these on your own and see if you come up with the right answer. Okay, I'm back. How did you guys do? So round 12.2105 mils to 5 significant figures, right? So here we have a 0. That's our makes our 5 significant figures. The next digit over is a 5, so we have to round up 1. So this is going to be 12.11 mils. 78.824 grams to 2 significant figures. So it's just going to be the 7 and the 8. We see the next digit is an 8. That's greater than 5. So we're going to have to round this up to 79 grams. 1,255.5 kilograms to 4 significant figures. So it's going to be 1,255, but the next digit over is a 5. So again, we have to round this up. Okay. And now I'm not going to read this, you guys. Sorry. But you can see we want to round this to 3 significant figures. These zeros, remember, are not significant because they place the decimal. These zeros are significant because they're part of the measurement. And if we want to do 3 significant figures, we're looking at 560, but the next digit to the right of the 0 is 9. So that means we're going to round this up to 0.00561. Okay. And then 2,501 grams to 2 significant figures. Now this creates a little bit of a problem, because if we just write 2,500, right? If we just write 2,500, because this 0 is obviously less than 5, so we're going to retain the 2 and the 5. If we write 2,500, that's going to be ambiguous because we don't know whether those two zeros are significant or not. So we would have to either write this as scientific notation, 2.5 times 10 to the third grams, or you might remember that 10 to the third can be represented by the prefix kilo, so we could also write this as 2.5 kilograms. Now, let's put all this together and solve a couple of problems, okay? So again, I want you to solve the problem, present the answer with the correct number of significant figures. All right, so I'm going to count to 3, stop talking, count to 3, and then come back and see how you guys did. So pause the video and give it a shot. Okay, back. Here we go. So we have 45.670 grams divided by 25.1 mils. So the 25.1 mils is going to determine the number of significant figures in the answer, which will be 3. When we do the division and the roundup, it'll be 1.82 grams per mil. Okay. Next, 2.34 minutes times 60 seconds per 1 minute. Remember, 60 seconds per minute is a conversion factor, so essentially it has an infinite number of significant figures. So the 2.34 will determine the number of sig figs in our answer, 3 significant figures. And so if we do that, it will be 140 seconds. And notice I put the decimal point there to indicate that that 0 is significant. Otherwise, we'd have to write 1.40 times 10 to the power of 3. Okay. And now we have 5.0250 grams times 0.4568 centimeters divided by 10.21874 minutes. So our 0.4568 centimeters is going to determine how many significant figures are in the answer, because that's the least number of significant figures of all of these. So 4 significant figures will be in the answer, and our answer is 0.2246 gram centimeters per minute. None of these units cancel out, so you have to leave them in their proper location, numerator or denominator, in your final answer. And then last, we have 3.56 times 10 to the 6th cells divided by 100.00 mils. Now, this is where things get a little confusing. When we count cells, yes, we are counting cells, and there is no half a cell or 1/5 of a cell or 0.2 cells. But whether you count cells manually through the microscope or you use an automated cell counter, you still have some variability. There's still some uncertainty because it's difficult to always catch all the cells. So we're going to treat this as if it's a measured quantity, not an exact number. And so there is some uncertainty associated with counting cells. So when we look at which number will determine the number of significant figures in the answer, we have 3 for the number of cells and 5 for the volume. So we'll have 3 significant figures in our answer, and this is just going to be 3.56 times 10 to the 4th cells per mil. Time to look at addition and subtraction. So this is still pretty easy, but you kind of have to shift your mind around from everything we just said. So when you're adding or subtracting measured quantities, the number of decimal places in the answer is determined by the number of decimal places into quantity with the least number of decimal places. So you have to look at the numbers and see how many places past the decimal each number goes, right? The least number of places past the decimal, that's how many you can have in your answer. All right. So again, if we look at this, 5.345 grams plus 4.25 grams, the 4.25 determines the number of places to the right of the decimal, because here we're 3 places to the right of the decimal with 5.345, and here we are 2 places past the decimal. So now the total number of digits doesn't matter. It's only the digits that are to the right of the decimal point when we are doing addition and subtraction. Okay, all right. So 138 mils minus 0.345 mils, right? There's no places to there's no digits to the right of the decimal point with 138. So the 138 determines the number of places to the right of the decimal point, which will be none. It will be 0. All right. So again, it's not the total number of significant figures. It's not the total number of digits, but only the number of significant figures or digits to the right of the decimal point that determines our number of sig figs in addition and subtraction. Okay, so let's give this a shot. Indicate which measurement determines the number of significant figures and do the calculation. Counting to 3, turn the video off, give it a try, and let's come back. Okay, I'm back. All right, so if we look at this, the 15.1 determines the position, how many digits are to the right of the decimal point. 54.70, that's 2 places to the right. This is 1 place to the right. So our answer can only have 1 place to the right of the decimal point, which makes it 39.6. Remember, this was a subtraction. 734 plus 215.28. The 734 has no places to the right of the decimal point. So our answer can have no places past the decimal point. So this is simply going to be 949 mils because 2 will be the next digit to the right of our significant figures. 2 is less than 5, so there's no roundup. And then here we have 200.00 grams plus 0.89 grams. Both of these are 2 places to the right of the decimal point. So our answer will be 200.89. Right, and then we have 13.5695 plus 36.202, 4 places to the right of the decimal point, 3 places to the right of the decimal point. So our answer can only have 3 places past the decimal point, which gives us 49.772. Okay, and now the last one was just to see if you were paying attention to details, because if you look, we have 5.978 grams plus 34.5 mils. These are not the same units, so we can't do the calculation. Okay? If you think for a minute, with a little more information, you actually could do this calculation if you think about it for a minute. You need one more piece of information. Right? Are you guys thinking about what it is? Okay, it's the density. If we know the density of this liquid, the grams per mil, then we can convert this number of mils into the equivalent number of grams, and then we can add grams to grams. So remember, in addition and subtraction operations, the units must be identical. When we're adding or subtracting, the units must be identical, and if they're not identical, you need to make them identical if possible. If not, then you can't do the calculation. All right, so let's see if we can do this, right? Here's our practice slide, and I'm gonna again count to 3 and stop talking, and then come back on and give this a shot. Okay, so you notice I set this table up to help ensure that you check for the consistencies of units, okay? So are the units consistent? Yes. Sig fig determination, the 19.8, right? 1 place past the decimal, so it's going to be the nearest 0.0. The correct answer with the correct number of sig figs would be 40.8 grams. Next problem, right? We're doing arithmetic. So we need to check to see if the units are consistent. They are. They're both in mils. All right. 545.228, 3 places past the decimal. 45.8971, 4 places past the decimal. So we're going to be the nearest 0.000. Right. So our answer is going to be 499.331 mils. Okay. Now Next one, 1.008 grams plus 37 milligrams. Are the units consistent? No, both must be in grams. But we can do that by converting milligrams to grams. And so now we have 1.008 grams plus 0.037 grams. And now both of these are 3 places past the decimal point. So our final answer is 1.045 grams. All right, next one, 75.00 grams divided by 3.1 mils. Now we're doing multiplication or division. The units do not have to be identical, but if they don't cancel out, the units have to be in their relative position in the answer. So the consistency of units is not applicable here, right? The 3.1 has 2 significant figures. So now we're not worried about how many places past the decimal because this is division. We're worried about the total number of significant figures. So here 3.1 determines how many significant figures. So our answer is going to be, when we round this up, 24 grams per mil. Next one, right? 45.23 centimeters times 2.634 centimeters. Since we're doing multiplication, the units do not have to be consistent, but we must retain the units. So again, since we're doing multiplication, it's the total number of significant figures that determines the answer. That is, whichever value has the least number of significant figures, that determines our answer. Both are 4 significant figures, so our answer must have 4 significant figures. And we have centimeters times centimeters, so that's centimeters squared. Next, 0.0234 moles divided by 250.0 mils, right? So again, this is division, so we don't need to have the units consistent. We then look at the total number of significant figs, and 0.0234, the 234 are the significant figures. This 0 is not significant. Okay, so our answer is going to have 3 significant figures. And I put this in scientific notation since it's such a small number. All right, next one. 0.6500 grams times 1,200.00 centimeters. So again, it's a multiplication. So the total number, so it's the total number of significant figures and the smallest, with the smallest number of sig figs determines the answer. This would be 6,500, 4 sig figs in the answer. So our answer is going to be 780.0 gram centimeters, right? It's just grams times centimeters. So they don't cancel out, so they stay there. Okay, 5 rat livers times 12 grams, right? So rat livers are exact numbers, right? We're multiplying, so we don't need to have matching units, right? 12.0 grams, that's our measured value. So there's 3 significant figures, so it's going to be 60 grams of rat livers. And then here we have a subtraction. We have 1.25 liters minus 512 mils. The units are not consistent, so we need to convert the units to be the same. And I've chosen to convert them into liters. So now we have 1.25 liters minus 0.512 liters. And here we have 2 places past the decimal. And here we have 3 places past the decimal. So it's going to be the nearest 0, and so our answer is 0.74 liters. And then the last one, just to see if you remembered from the previous example, 4,000 seconds plus 75.23 millimolar, 4,000 seconds plus 75.23 millimolar. Okay, the units are not consistent, so you can't solve this problem. And that is the end of segment 7.